I want to welcome you to my lecture today. Those of you online, I needed to confirm if you are hearing me clearly. Are you hearing me clearly?
Yes.
Okay, thank you for confirming that. And those of you at the back, can you hear me? Okay, thank you so much. I want to welcome you to a new week. And I also want to welcome you to this topic. The other time, we started something that has to do with the central limit theorem. And I want to tell you the central limit theorem is very, very important in statistical analysis. And of course, I actually walk you through, you know, how central limit theorem applies to some real life practical problems. I remember on Friday, I walk you through the central limit theorem, how it works with mean. But the focus today is actually going to be how central limit theorem work with proportions. And I quickly want to remind you that the essence of investigating, the essence of going into population is to actually provide a response to practical problem. I want to tell you that what we're looking for is what we call parameter. I told you the other time, parameter is an unknown population characteristic value. The parameter could be mean, it could be proportion, it could be variance, it could be standard deviation. And one example of a parameter is when I'm trying to look at, maybe I want to determine the average household income in a particular country. Okay, so that's a parameter because it's an unknown. So another parameter could be I actually want to investigate maybe how many people in a particular country actually approve the job the president is doing. Of course, in that situation, the parameter is a proportion. So what we want to do today, the focus is actually going to be on proportions. But let me tell you this. What is the essence of a central limit theorem in statistics? You know, let me first state the theorem. The central limit theorem is just like if we have a population that we actually want to study, and the population has mean and variance, then the sampling distribution of means will actually be normally distributed. I'm going to say that again. You know, the population we're choosing from does not necessarily need to be normal, but provided we choose a very large, sufficiently sample, and how large is a large is at least story. Now, the implication of central limit theorem in statistics discipline as a whole and in research in general is that the central limit theorem enables us to use statistical method or probabilistic method applied to normal distribution to other form of distributions. I'm going to say that again. Let me tell you this. In statistics generally, all statistical method can be classified into two. Some method, they are appropriate where the distribution is normal, distribution of data set. Why other method is when it is non-normal. But you know what? The central limit theorem will enable us to use statistical methods, okay, applicable to normal situations to other distributions that are not normal, but provided we took a sufficiently large sample. Okay, like I said, the outline today, we're actually going to use central limit theorem to find probability for sample proportions. The first objective was achieved on Friday, where we're focusing on the sample mean. Okay, but the second objective is what's going to be our focus today. Now let's get started. I want you to be seeing this. I want us to apply this to real life practical situation. For instance, I want to know the number of people with a certain trait. That means I'm not interested in the entire population. I'm only interested in a certain part of a population. Then the parameter of interest is proportion. I'm going to say that again. When the interest is not on the generality, when the interest is on certain parts of a population, then the parameter of interest is actually going to be proportion. Okay, and you know what? The parameter of interest, if we have access to the whole population, which I know we don't, then it's actually going to be this formula here, which is N is totality and X, the numbers of individuals in the population that possess certain characteristics of interest. A very good example of this, I want to determine or maybe popularity of a sitting president. Of course, my target population will be all electorate, all eligible voters in that country. All eligible voters in the country, they say, it's uppercase N. X will be the number of them that actually approve the job the president is doing. But like I said, we don't carry out what we don't carry out what I call 100% enumeration. We're actually going to take a sample. When we take a sample, this is what we got. This is the formula we're actually going to use. Anytime you see a cap, look at that. That's a cap on P, right? That actually indicates sample proportion. I'm not going to study everyone in that country. I'm only going to take a sample size. And you can see here a lowercase n actually represents the sample size. And a lowercase x actually represents the number in the sample size that possess the characteristics of interest. Take a look at that. Okay, now, we want to talk about, let me tell you this. I think I justified the excess of sampling distribution the other time. Did you know that if 5 investigators should conduct research on the same team, they're actually going to have a different value for this P cap. And that is the reason why election, a particular election was conducted in the, was it Virginia, yeah, a gubernatorial, I think last Tuesday. And I know before the result, there was opinion poll, right, conducted by different organizations. If you check on different organizations, when you check on the website, they're going to have a different value for P. Because The reason why they have different values for P, of course, they were selecting at random. They're going to make use of different participants. And how are we going to know which one is the correct one? To be able to know the correct one, what we're just going to do is to find the mean of that. That is what we want to do now. Take a look at that. We actually want to talk about the mean and the standard deviation of a sampling distribution of a sample proportions. Take a look at that. We have more than one sample proportion. Then the sample proportion become random variable. When you have more than one sample proportion, then it becomes random variable. Then we can begin to look at the mean of that. And we can begin to look at the standard deviation of that. But let me tell you this. We have conditions under which we can actually, apply central limit theorem with a sampling distribution of proportion. Take a look at this. The whole thing is a binomial situation, because if I ask one person, do you like the job of the president or not? It's either you say yes or no. That is categorical. Now, and the only way to apply this is when the product of N and P is greater or equal to 5, or when the product of N and 1 minus P greater or equal to 5. You remember the other time where we were dealing with the normal approximation to binomial, right? There was a condition that needed to be satisfied. You remember that, right? Now, this is a condition here, which is a condition to be applied before we can actually assume a normal approximation to binomial. So what I'm trying to say here is, when the samples taken as simple random samples, the condition for a binomial distribution are met, and the sample size is large enough to ensure that. In the case of mean, the sample size, we focus on the sample size. We said the sample size has to be at least 30. But in the case of proportion, the focus is going to be on the product of N and P. It has to be at least 5. Yep. Yeah, the P is a population proportion. Well, that's a very good question, because we have two types of P. One is sample proportion, the other one is population proportion, and it's asking about what kind of P are we are we talking about in the requirement? It is population proportion. Okay. Now, when I have several values of P proportions, maybe MSBC give us the popularity of the president. The Fox News gave us the popularity of the president. We have different kind of news that gave us popularity. Then the mean of that is what this guy is talking about. The mean of the sampling distribution of sample proportions. I'm going to say that again. The mean of the sampling distribution of sample proportions is actually going to be equal to P. The standard deviation of the sampling distribution of sample proportion is the square root of P into 1 minus P divided by N. And you know what? This guy here is also called the standard error. The standard error of proportions. I just wanted to take note of that. Okay. The next thing that we now need a z-score. Let me tell you this. For you to apply, if you want to get a z-score has a special requirement. The requirement for a z-score is that the statistic under investigation is normally distributed. If that doesn't hold, then you can make use of a z-score. But the only way to investigate this is what we've done before. The product of n and p has to be at least 5. And the product of 1 minus p, n and 1 minus p, has to be at least 5. The moment that condition is met, then we can actually apply a z-score for proportion. Okay, now when you take a look at this, this is the formula now. Now, this very z-score is just the difference between the sample proportion and the population proportion divided by the standard error. But I wanted to take to pay attention to this guy now, the guy in the square root. That guy in the square root is not a sample proportion, it's a population proportion. Take note of that. The guy inside the square root, I'm talking about the p here. The one that have a cap is a sample proportion. P without a cap is a population proportion. So what I just show you now, it's actually how to figure out how z-score, okay, where we're dealing with a sampling distribution of proportion. Now, of course, I'm trying to redefine. What I'm doing on this slide is just to tell you what each particular notation represents. Okay, the p cap is actually the sample proportion, and p is the population proportion, and n is the sample size. Now, I want to walk us through an example now. Let me tell you this. Just like what we did on Friday. On Friday, we were focusing on the sample mean. I could remember we did. What is the probability of a sample mean? Less than? What is the probability of a sample mean? Greater than? What is the probability of a sample mean falling in between? What is the probability that a sample mean would differ from the population mean by more than a given amount or by less than a given amount? That was what we did on Friday. Okay, we're also going to do the same here. Okay, now take a look at the first example that I want to talk about. Finding the probability that a sample proportion will be at least a given value. At least a given value is the same thing as greater than or equal to. Okay, and we can also treat that as greater than too, because we're talking about continuum, because we're using the knowledge of a normal distribution. And you know what? Normal distribution is a continuous type distribution. Therefore, there is no difference between greater than or greater or equal to. They are the same. So at least it's the same thing as greater or equal to, which is also the same thing as greater than. You know, when the random variable is actually continuous in nature. Now take a look at this example. In a certain conservative precinct, 79% of the voters are registered Republicans. What is the probability that in a random sample of 100 voters from this precinct, at least 68 of the voters will be registered Republicans? Okay, now, and we have, this is the first thing you're going to do. You need to get your sample proportion. You get your sample proportion from the data set. You have been told that out of 100 sample size, and you have been told that 68 of them, you know, you want to find the probability of at least 68 of them will be registered Republican. Of course, using the formula that I showed you before, that P cap sample proportion is actually going to be the ratio of the number of the characteristics of interest to the sample size. Here is going to be 68 divided by 100. That will be 0.68 in decimal, and that will be 68% in percentage. Now, what do we want to do? We want to find the probability. You know, when you take a look at the normal distribution, you were given a center you were given the population proportion. Take a look at that. The population proportion before investigation, the value of the proportion before investigation, before you took a sample size at all, that was a population proportion. That was 79%. And that 79% is going to be the center. Look at that. That is the center of the normal distribution. And you want to find the probability of at least 68%, at least 0.68. It means you are looking at that to the right of the distribution, right? And if you are looking at that to the right, now you need to collect your data set. Okay, then you need to make use of the z-score. That's a z-score formula. Or what you just need to do is to plug in those values. You plug in the sample proportion, the population proportion. I told you the other time what you have inside the square root. They are population proportion. You can see when it's 0.79, it's going to be inside the square root. At the end of the day, I'm actually going to get my z-score. The z-score that we have is minus 2.70. And the next thing we're going to do now, we actually want to find the probability of a z-score greater than minus 2.70. Because what we are given in the question is to find the probability of the sample proportion greater than 0.68. And that probability would be equal to the probability of a z-score greater or equal to minus 2.70. Now, where we are now, this is where we normally make use of a table. We make use of a statistical table, or you make use of your calculator, or you make use of your software. Okay, so when you do that, it's actually going to give you 0.9965. Okay, because why? If you want to use our software, it's going to be 1 minus p norm of minus 2.70. 1 minus p norm of minus 2.70. Why am I saying 1 minus p norm? Because I'm talking about greater than. And if you want to use a calculator, this is how you're going to specify. For those of you that want to use calculator, okay, so take a look at that. The very first thing I'm going to specify for greater than would be that particular sample proportion is 0.68. To infinity, the center, that is population proportion, and the standard error. And at the end of the day, the calculator will automatically compute that. Then you're going to have your result. Whichever method you want to use, you are free to use whatever method you are comfortable with. Now, always make sure you have a conclusion. You interpret your results. The probability of at least 68 voters in a sample of 100 being registered Republican is approximately 0.9965. That probability is kind of very high, right? So that's what I mean. Now, this is the next question. The first question was talking about greater or equal to. This question is going to talk about less, because it says, finding the probability that a sample proportion would be no more than the given value. That's a less or equal to. You're actually going to do the same. This time around, I say no more than 80. You proceed again, you calculate your sample proportion. Then after getting the sample proportion, you want to, this time around, you are looking at that to the left. Okay, this is your focus. You're looking at that to the left. The center at this time is actually 0.81. If you take a look at what you're given in this principle, 81% of, this time around, we are no longer talking about Republicans, but we are talking about Democrats. Take a look at this. So in this particular principle, 81% of the voters are registered Democrats. That's its population proportion, 0.81. And you actually want to find the probability that in a random sample of 100 voters from this principle, no more than 80 of the voters will be registered Democrats. Okay, so that is what we're doing. We're going to follow the same thing. You plug in the values, I got my Z score. But this time around, we're dealing with the less than, right? Whatever you check from the table is your result. Or if you want to use our software, you're actually going to say P norm of minus 0.25. Okay, and that will give you 0.4013. And I provided an option for you if you actually want to use an scientific calculator. Now look at where I'm starting from. The cause is a less than, it's a leftist, it's to the left. I'm going to start with the negative infinity. Okay, to 0.80. I'm going to specify the population proportion and the standard error. And of course, the calculator will automatically compute that. Whichever method you want to use, you're still going to get the same result. Okay, now this another example that we want to consider now. We want to find the probability that a sample proportion will differ from the population proportion by less than a given amount. You remember on Friday, we actually find the probability that the sample mean will differ from the population mean by less than a given amount. But right now, the parameter of interest is no longer mean, but proportion. Okay, now let's leave politics now, and we want to go into an example in medicine. It is estimated that 8.3% of all Americans have diabetes. Suppose a random sample of 74 Americans is taken. What is the probability that the proportion of people in the sample who are diabetic differs from the population proportion by less than 1%? How do we approach this? We actually, just like what we did on Friday, we subtracted that amount from the center. We also add the amount to the center, right? The center here is actually 8.3%, which is 8.3 divided by 100, which is 0.083, right? We're actually going to subtract the 0.01 from that. We're going to add the 0.01 to that. And that is actually going to give us two values, the lower point and the upper point. The lower point is going to be 0.073. The upper point is going to be 0.093. If I want to display that using the normal curve, this is what I'm trying to say. Look at that. The center is the one. Look at the center and look at the two, the 2 points. Okay. And what do we actually want to do? We actually want to find the probability, okay, between the 2 points. Okay, so we needed to find a z-score. We're going to have two different kind of z-score. Okay, now take a look at that. We find the first one. Of course, in this kind of situation, since we're talking about difference, you have already been given the difference. It's 0.01. That is the difference between the sample proportion and the population proportion. And automatically, when you do that, you get 0.31. And let me tell you, you're going to get, just like what I showed you on Friday, you're actually going to have two z-score, but they're going to be the same number, but only in opposite direction. Take a look at this. It's going to be minus is 0.31 and a positive is 0.31. So how are you just going to do? You want to do so on our software, it's going to be the P norm of one minus the P norm of the other one. And of course, if you want to use a calculator, what you're actually going to do, you need to specify the lower part, the upper part, the center, and the standard error, and automatically the calculator will compute that. Okay, the next one is finding the probability that a sample proportion differs from the population proportion by more than a given amount. And we want to look at this example. It is estimated that 8.3% of Americans have diabetes. Suppose that a random sample of 91 Americans is taken. What is the probability that the proportion of people in the sample who are diabetic differ from the population proportion by more than 2%? Anytime you're talking about more than 2% and they differ by that amount, you are looking at the tail. not something between. We're still going to do the same thing by subtracting a 0.02 from the population proportion, and we're going to add the 0.02 to the population proportion, and you're actually going to have two bounds, the lower bound and the upper bound. And I want you to take a look at the shape right now. The lower bound is going to be 0.063. The upper bound is going to be 0.103. This time around, we are not interested in the yellow shaded region. That is not our interest. Our interest is actually on the tail, because we're talking about more down. Okay, so that is our interest, and what are we going to do? Okay, we're also going to get a z-score in this situation. There are going to be two different values for z-score. It's 0.69 and minus is 0.69. You just check for one, then you multiply by 2, then you have your result. And if you want to use our software, the R software is going to be 2 multiplied by 1 minus P norm of a positive z-score. I'm going to say that again. If you want to use an R software, it's actually going to be 2 multiplied by, 2 multiplied by the parenthesis of 1 minus P norm of the positive 1. And if you want to use your calculator, it's actually going to be 2 multiplied by normal CDN. You're going to put infinite, negative infinity. You're going to put a 0.063 and a 0.083, which are the lower bound and the upper bound. Then you're also going to put a standard deviation of the proportion, which are actually called the standard error. Then the calculator will automatically compute that. Now, if you take a look at what we have done today, the takeaway is actually, we just repeated what we did on Friday. That is what we just did. We repeated what we did on Friday, only that the parameter of interest today is different from the parameter of interest on Friday. The parameter of interest for Friday was a sample mean, but the parameter of interest today was a sample proportion. Whether we're dealing with a sample mean, we're dealing with a sample proportion, the central limit theorem applies, provided the condition underlying the use of central limit theorem applies. And what we need to do is to first investigate whether the condition underlying the use of central limit theorem apply, because let me tell you this, if the condition underlying the use of central limit theorem does not apply, you cannot, when you go ahead and find a z-score, that will never be correct. It's you actually going to mislead. Because in statistical, in statistics in general, we don't just use method, we have assumptions. All method in statistics have assumptions. And before we can actually use a particular method, assumptions need to be met. Okay, if you bother not to investigate whether assumptions are met, then I'm going to tell you it's risky. Okay, and that is the reason why at times in real life practical situation, it may look as if our models are failing us. But you know what? Our models are not failing us. We are the one that we're not doing the right thing. So why are we not doing the right thing? Because we don't really care to investigate whether the assumptions underlying the use of a model is met or not. A philosopher said, and I quote, when the premise of an argument is false, so the conclusion. Because the requirement of using a certain statistical method is not met. If you go ahead and use the method and you actually make a recommendation from such study, the recommendation will be misleading. Okay, the recommendation will never see the light of the day. And that is the reason why we need to care much about investigating the validity of the method we're using. Is my method appropriate or not? We have a way to investigate that. Statistics is complete, very, very complete. We have a provision for all of that, but only that most of the time, some of us are in a hurry. We don't even bother to check whether the assumptions are hold or not. So the takeaway from what we have done today and what we did on Friday is that the central limit theorem has a role in statistical analysis because, I told you the other time, if the population we're choosing sample from is normally distributed, of course, irrespective of the sample size, we're actually going to choose the sampling distribution of the whether sample mean or sample proportion will be normal, because the population we're choosing from is already normal. But what if in a situation where the population we're choosing from is not normal? Some of you may be wondering, how do I know if it is normal or not? We're actually going to plot histogram. We have a way to check whether it is normal or not. If it is not normal, and in a real life practical situation, we don't expect, most of the time, I'm going to say the distribution of the population is non-normal. Most of the time. Then what do we need to do? Okay, if it is not normal, we don't need to worry about anything. Depending on the sample statistic we are investigating, or depending on the parameter we are investigating, if we're investigating parameter population mean, which means we actually want to talk about sample means, then provided the sample size is 30, okay, then we can apply the central limit theorem applies. If central limit theorem applies, then you can proceed. That's a pass for you to compute your z-score. Because when you compute your z-score, don't forget, it does not end there. The underlying probability distribution you're going to check your z-score from is a normal distribution. When you see z-score from the table, or when you check the probability from the table, or using a software, or all of that, is you are checking them from the normal probability distribution, and that is the reason why there's that requirement. If you're talking about sample proportion, the only way to know whether the central limit theorem applies is when the product of the sample size and the population proportion is at least 5. Or when the product of the sample size and 1 minus p is at least 5, the two of them have to be satisfied simultaneously before I can now say the central limit theorem applies. Okay, this is where I'm actually going to stop today, but let me quickly tell you this. I've already uploaded the solution to the midterm 2 practice question that I uploaded the other time. I noticed some mistakes. Some mistake that the question like based on number 11, and maybe the question said based on 13. I'm very sorry. I sincerely apologize for that. But now I've posted, the solution to the midterm 2 practice question. For those of you who attempted those questions without solution, you can grade yourself. Okay. And on Friday, our focus is going to be on the midterm 2 practice question. I'm going to go over that together with you on Friday. And I'm also going to tell you some information about the midterm 2. And I'm going to tell you some other, things information you are expecting about midterm 2. Make sure you stay safe and have a lovely day.